yesterday our aim was try to understand Schwarzschild black hole, particularly how the light behaves and how can we construct a coordinate system which is well behaved at the r equal to 2m surface. Okay. And something we have tried using what is called the ingoing light coordinates, the ingoing Eddington-Finkelstein coordinate. And we have found that if I use the ingoing Eddington-Finkelstein coordinate, so instead of t r theta phi, usual spherical symmetric coordinate, we have gone to v r theta phi, where v, this is the meaning of v, it represents ingoing light ray. The coordinates on v equal to constant surfaces are ingoing light rays. Okay, that we have seen. And then what you have found that the metric is given by 1 minus 2m by r dv square plus 2 dv dr plus r square d omega square. Okay, good. So this is what the metric is. Sorry. And we have found that although this metric is defined only for r greater than 2m, as such this metric is also valid beyond r equal to 2m to the other smaller values of r. So therefore what we can do is that although we have defined this for r greater than 2m, we can use this metric, particularly this coordinate, adapted to the ingoing light rays beyond r less than 2m. Okay, that means we can go enter the r equal to 2m surface. What is also important to understand that we found that we can enter the r equal to 2m surface, but the causal structure is such that we cannot come out. In fact, what we found is that the light rays at r equal to 2m surface are of this type. This is r equal to 2m, this is r, sorry, and this is v. The ingoing light rays is always v equal to constant, and outgoing light rays at r equal to 2m becomes the r equal to 2m surface itself. Okay, so it means you can always go inside on a future directed curve, but if you want to come out, you have to move faster than the speed of light locally. Okay, and that is not possible. Okay, so therefore this shows that r equal to 2m is a causal boundary. Causal boundary. So by riding on an ingoing light ray, you can enter into the r equal to 2m surface, even go inside to the r equal to 0, God knows what is happening there. Okay, but you cannot reverse. Okay, and we have explicitly proven in a coordinate independent way using the only notion of space-like and time-like thing. Give me a second. Space-like and time-like, space-like and time notions of space-like and time-like vectors. We have proven that for r less than 2m, non-space-like curve and non-space-like curve we found that dr dv must be greater than equal to 0. Okay, and for future directed curve, if you want to move along the future direction, that is all we can do. Future directed curve, dv is positive, and therefore we must have dr less than equal to 0. And the equality sign hold only when r is equal to 2m. So let's think of that r is not equal to 2m, r is less than 2m. In that case, the equality sign does not hold, and what we have r less than 2m. Which means that I cannot decrease r. Okay, okay. I cannot decrease r. I cannot decrease r. I can only decrease r once I'm inside the r equal to 2m surface. I cannot change my course of my spaceship and come back out of the surface r equal to 2m once I inside. What it means is that there is no time-like curve or the light-like curve connecting points inside to outside. Okay, good. This is fine. Okay, so this clearly proves that r equal to 2m surface is a causal boundary of the black hole. But there is also something more we need to prove, okay? And something more we need to go ahead, okay? Now, first of all, it seems to us that, look, this is a bit strange situation because I know that the general relativity is dictated by Einstein's equations. They are time symmetric, second order differential equations. So why would I am getting a solution which seems to be only allow you to enter into a one-way surface, okay? What is the time t2 minus t version of this solution, okay? To get this, let us now use, okay, instead of the ingoing light rays, let us now use outgoing light rays, okay? So now let us use outgoing light rays, outgoing light rays, light rays, and adopt, sorry, adopt u equal to t minus, sorry, equal to t minus r minus t minus r star as one of the coordinate. Okay. So earlier we were using, instead of tr theta phi, we are using vr theta phi. Then what we here we will do is that we have this, we will use ur theta phi. Okay. So we will use the u equal to constant surfaces again represent outgoing light rays. So if we move along u equal to constant surface, we move along the outgoing light rays. Okay. And you can immediately check how does the metric look like in this coordinate system. Let me write down the metric. Remember, there is a crucial minus sign between t and r for the definition of u, whereas v is defined as t plus r star, u is defined as t minus r star. And that minus sign changes a little bit the metric in this coordinate system. And it ultimately looks like minus 2 du dr plus r squared d omega squared. Okay. So this is the metric in this coordinate system looks like. Now let us understand, when I use this coordinate system, what is the property of r less than r equal to 2m surface. Okay. So how do we do that? Again, the same idea. We look for the light rays. Okay. Look for, understand, or analyze radial light rays. Okay. And how does radial light rays behaves? It's very simple. For radial light ray, we said ds square equal to 0. Okay. So we said ds square equal to 0 and d theta, d phi all equal to 0. Okay. Because I'm thinking about how radial light rays behaves. Theta and phi remaining constants. Okay. If you do that, immediately you will find, just like previously we find dv dr, here we will find du dr. On the light ray, there are two solutions. One is 0, which implies u equal to constant, and therefore this must be the outgoing light rays. Outgoing light rays. And therefore the other solution, which is, you can immediately verify, will be this, and this must represent the ingoing one. Okay. Just like the previous case, we solved for the ds square equal to 0 equation, and we found the ingoing and the outgoing light rays. Let us be here, and let us understand what happens to the previous argument here in this case to understand the properties of the r equal to 2m surface. We also note, just like the previously, here 2 du dr, this is given by minus ds square plus 2m by r minus 1 r square d omega square. Okay. Therefore, you notice that if r is less than 2m, ds square less than equal to 2m. Remember, we are using minus plus plus signature. So in our signature, non-space-like curves obey ds square much less than ds square less than 0, less than equal to 0. Okay. You will immediately see that 2 du dr, okay, must be positive. Okay. This is the difference. Earlier 2 dv dr, remember, it turns out to be negative. But in this coordinate, it seems 2 du dr is positive. Okay. Again, we can only use the future directed curves. For future directed case, future directed, that means du is positive. Okay, you will find dr to be positive. Now this is exactly opposite to what we have learned previously. Earlier I have learned that in VR theta phi coordinates, r equal to 2m surface has dr, once you are inside, dr is negative. That means all all non-space-like curve radius must decrease. You cannot increase the radius. You are from once your r less than 2m, you cannot come out by increasing the radius through a non-space-like curve. Here it's totally opposite. It says once your r less than r equal to 2m, you have to increase your radius if you want to move on a non-space-like curve. So it means, it seems to suggest r equal to 2m surface, everything comes out. Everything can only come out. Nothing can enter. Now this is very, very paradoxical, because we have used the ingoing light ray, and then we have found that the causal structure is such that I cannot come out of the r equal to 2m surface. But when you are using outgoing light rays, it seems the causal structure is such that we cannot enter the r equal to 2m surface, we have to come out. In fact, if you draw the light cones here, let us draw the light cone here. How does the light cone will behave in this coordinate system? Okay. So this is u, this is r. Remember, outgoing light rays here is always u equal to constant. So let's draw the outgoing light rays. This is my outgoing light rays. Okay. Okay. So this is always outgoing light rays. So ingoing light rays, the slope is changing. Okay. If you are convince yourself, if you are inside, the slope will be like this. Okay. Once you close, so this is r less than 2m, this is r greater than 2m, and this is r equal to 2m. Okay. Once you are at the r equal to 2m, the outgoing light rays still remain u equal to constant. Okay. But the slope has tilted. Note, the slope is a function of r for the ingoing light rays. Okay. Okay. Clear? I hope these things are clear to everybody. And then you can write down this light cone structure to be like this. Okay. Now you can see, you can only go out. Okay. Okay. You cannot enter. Okay. You cannot enter. So if you want to enter here, you have to cross the light cone. That means locally you have to move faster than the speed of light. That is not allowed. Okay. So in one case, when I'm adopting to light rays which are ingoing, it seems to me r equal to 2m surface is a causal boundary allowing only to enter, but not allowing to come out. Other case, when you're using outgoing light rays, it seems r equal to 2m surface will only allow things to come out of it. Okay. So this is very strange. What is the property of r equal to 2m surface? It seems to be depending on which coordinate I'm using. This paradox can easily be resolved by understanding that by using ingoing and outgoing light rays, you are actually reaching at different points in space-time. So let's understand that. Note that when you are using v equal to constant or t plus r star equal to constant, when you are on the outgoing, when you are on the ingoing light rays, that is V equal to constant, okay, R is decreasing. So to keep V constant, T must increase. Okay. In fact, R is decreasing, and T should increase. Okay. And what is the maximum value T should reach? You can go up to T goes to infinity. Okay. So on ingoing light rays, you can ultimately reach T goes to positive infinity. Okay. The future. So that is very important to understand. So what is happening is that when you are reaching ingoing light rays, V equal to constant, you are reaching a region in space-time which is T goes to positive infinity, asymptotic future. Okay. Now note, when you're using outgoing light rays, while for outgoing light rays, okay, U is equal to T minus R star equal to constant. So if you're moving in the decreasing direction of R, okay, T should also decrease. Okay. So when you're moving along, or in other words, moving along U equal to constant surface towards R decreasing, will take you to T goes to negative infinity. So what is happening is that in this case, you are actually coming out of, so this is outgoing light rays, U equal to constant, and this is some R equal to 2m, and you are coming from T goes to negative infinity, the past. Okay. So basically, the regions, when the future of the ingoing light rays is the region inside the R equal to 2m, but time-wise it is in the future. The past of the outgoing light rays is again inside R less than 2m, but it is coming from the distant past. So by using ingoing and outgoing light rays, while entering into R less than 2m, you are actually entering into a different region in space-time. You have discovered completely different region in space-time. So if it is R equal to 2m, just cartoon-wise, I am not putting much of a meaning of these lines at this stage. You can use ingoing light rays, cross R equal to 2m, and reach future. Okay. While as this is again R equal to 2m, you can use outgoing light rays, and they are coming from T equal to negative infinity past. Okay. So ingoing light rays goes to R less than 2m and reach the asymptotic past. What happens to do them, we'll discuss later. Maybe they will probably go, we have to think about what happens at the R equal to 0. Whereas outgoing light rays originates inside the R less than 2m, but in the asymptotic past. So by using light rays, you have discovered there is completely two different regions in space-time, depending on what light rays you use. Okay. So there is this region R less than 2m, but T goes to positive infinity. Okay. By T, one has to be a little careful because T is not really very meaningful inside the horizon. So you may say, you can go, so let's not write down any t here. So you call it that in some sense, the future. Okay. And here it is the past where still r less than 2m. Okay. And this is what is expected because these two, what is happening here and what is happening here, are exactly time symmetric version of each other. Okay. In this case, you can only enter r equal to 2m, go inside and cannot come out. For this case, you can only come out of the r equal to 2m, increase r, but cannot go in. Okay. And since Einstein's equations are time symmetric equation, we expect both of this solution to be expected. Of course, it's not obvious, it is not required that both will be physical solutions. Okay. These are mathematical solutions. One of them will be physical solution. And good example of it will be, say, for example, when you study electrodynamics, when you solve Maxwell's equations, we get both advanced and the retarded solution. Retarded solutions are what is called the causal solution because there the future is determined by the past. Whereas the advanced solutions are anti-causal solution where the past, okay, is determined by the future. Okay. Okay. And we used either the retarded Green function or the advanced Green function. Okay. Now the point is that although both the solution exists in Maxwell's theory, we only work with the retarded solution because that is the causal in nature. Why the retarded solution should only actually in nature is a completely different story which I'm not going into. But here what happens is that although mathematically both the solutions are possible, physically is actually the first solution matters. Okay, that is because when black holes form or things collapse, there is a particular direction of the collapse. Okay, and in that case, that breaks the time symmetry. Okay, so therefore, in that case, only the first solution when you can only enter but cannot come out, what matters. Okay, but technically both the solution exist, and in this case, the first solution we call it black hole, and the time symmetric version or the t2 minus t version we call it the white hole. So what we have found is that by using light, okay, if we use outgoing light rays, we come out of the white hole. If we use ingoing light rays, we go into the into the black hole. Okay, so we have completely discovered new regions. Earlier we only have r greater than 2m. We thought r less than 2m, that's all. But we found that r less than 2m can be reached in two ways. It could be in the past, light rays are coming out of it, or in the future, light rays are going into it. Okay, and both are perfectly acceptable solutions of the Einstein's equation. So what is important is that using null geodesic, we have discovered new regions in space-time which was not really covered in the earlier good old Schwarzschild coordinates. I'll stop here and take few questions. Please let me know if there is any question. I'll wait. If there is any question, please ask. You can write to the chat. Okay. How can we mathematically classify? We already know the equations of outgoing and ingoing light rays. So we just use, so what you should say is that what are the class of geodesics we have? Okay, so the general philosophy is this. We have timelike geodesic, we have null geodesics. I have not discussed the timelike geodesics because that does not really give us anything new more than what null and the space-like one gives. The philosophy is that you use the timelike, the null geodesic, and try to find what is the possible way you can extend your solution. Okay. Okay. We have so far used, there are only two possible null geodesics, the ingoing one and the outgoing one. Okay. So we have used both ingoing and outgoing null geodesic and found there are new region in space-time which is corresponding to t goes to positive infinity in the future or in the past. Okay. And these are what we call the analytic continuation of the space-time beyond r equal to 2m using geodesics. Okay. So first is called the future analytic continuation, and the second is called the past analytic continuation. Of course, the next question we will ask that, okay, null geodesics are fine. Can you use more analytic continuation? For example, if I use space-like geodesic, of course, space-like geodesics are not physical, but I can always use mathematically if there's space-like geodesic. The question is, do I discover any new region? And that is what is the aim of the Kruskal coordinates and what is called the maximum analytic continuation of the Schwarzschild manifold. Okay. So what we're doing is that we are using the tool geodesic motion to find how far we can analytically continue the Schwarzschild spacetime and discovering new and new regions. Okay. All the regions are need not be physical. In a physical gravitational collapse, we will see only 2 of the 4 regions in Kruskal manifold will matter. Okay. Next is the describe the wormhole. I have not described anything about wormhole. Wormholes are not coming here. I'm talking about white holes. Wormholes are objects with non-trivial topology. We are not going to discuss them in this class. A black hole is R equal to 2m surface when it is acting like a causal boundary, allowing things only to enter but cannot come out. Okay, so then it's the event horizon. A white hole is the time reverse version of the same solution when R equal to 2m surface is like a, it's a other way around. It's allowing things only to come out, but is not allowing things to enter. That solution is called a white hole solution because the opposite of black is white. White hole is a mathematical construct. It is there as a solution of the field equation, but most probably physically we will never see a black hole. A white hole. Okay. So there is a time symmetry between the formation of no. This is just this is nothing to do with the symmetry breaking in the sense of the condensed matter physics. Okay. It is nothing to do with the condensed matter physics. It is something to do with just saying that it's a T2 minus. It's like retarded versus advanced potential. How dr less than 0 explain nothing. So note that if I am in a space like, if I am in a time like curve beyond r less than 2m, say r equal to 2m, I mean r equal to 2m, sorry, r equal to m, which is inside r equal to 2m. Okay. If I have to move on a causal plus non-space like curve, r must decrease. That means, so suppose you are at r equal to 2m, you want to come out, if you are at r equal to m and you want to come out of the r equal to 2m surface, then you have to increase your r. Okay. You have to increase your r. Okay. What is saying is that to increase r, you have to move on a space-like curve. Nothing can move on a space-like curve. So therefore, once you are inside, you can only move along the direction of r decreasing. You cannot come back. Is this clear? Is it clear? Okay, I hope it is clear. Can black hole and white, I have no idea whether they exist in pair. There are some theories, but in a classical black hole scenario, collapsing scenario, the white hole is just mathematical construct. It doesn't exist. Okay, because when things are collapsing, when you go backward, you hit the surface of the collapse. Okay, then you are inside the matter. Okay, then the Schwarzschild solution itself is not valid. Okay, so therefore the white hole is just a mathematical tool in that case. Okay. No, there is nothing like repulsive, attractive. These are Newtonian words. Okay, these words has no value here. Okay, please understand, we are understanding the causal structure of the space-time. Okay, the causal structure of the space-time is dictated by the properties of the light cone. Okay? For the white hole solution, the light cone structure is such simply because there is a non-trivial mass energy density at the origin that nothing can enter into the white hole, but things can only come out. There is no such thing like repulsive force. Okay, it's the structure of the space-time which is dictating everything. Okay, so the Newtonian language is sometimes useful but not very illuminating. Okay, I have no idea what universe emerges from black hole and dies and what hole. No, I don't think these are right words. These are science fiction fantasies. Okay, I don't know what does it mean. Okay. Universe originates from, as far as the hot Big Bang model is concerned, it originates from a singularity. Okay, and we don't know. Okay. What is the problem of the tortoise coordinate system? Oh, that is because tortoise coordinate system does not cover what is happening inside the horizon. See, once you're on an ingoing light ray, the ingoing light ray can penetrate r equal to 2m surface. So there is a finite value of v by which you can go inside the r equal to 2m surface. Note that r star, there is no finite value of r star for which r is less than 2m. So moving using r star, we cannot do that. Okay. Good question. That v, so v is not space-like. Please understand that t is space-like. Okay. T is space-like. This is something. This metric is the metric which is a non-diagonal metric in v r theta phi coordinate. Okay. So if you move along the light ray on v or u, okay, they don't change the signature. The Schwarzschild time becomes space-like. T. Okay. Good question. Any other? Good. If there is no more question, I'm going ahead. Okay. Okay. So now what we have found is that using light rays, ingoing. Oh, what is a two-sphere? Oh, that, yeah, I request you look at any of the standard references. A two-sphere is a compact surface it's a usual geometric sphere. Okay, so the equation of a two-sphere will be, you take x, y, z coordinates and think of it is embedded in R3, and the equation of the surface will be x square plus y square plus z square equal to constant. Okay, that's the surface of a globe. That's all. Okay. Anyway, associated define, no, at this stage we are in the level of classical mechanics, classical theory. This has nothing to do with the entropy of a black hole. Entropy of a black hole is a completely different, unrelated, it's much more, it's not related to what we are talking about at this stage. Okay. Is there any more question? Okay, we can come back to questions later. Okay. What was your question? There is, okay. Please understand that the coordinate t becomes space-like. Okay. But v is or u are the coordinates on a light ray. They don't become space-like. Okay. They are null coordinates. They always remain nulls. That is why we choose them to enter into the black hole. Okay. Good. Good. Let's start ingoing and outgoing. We found two distinct regions. So the question is, if we use let's say space-like geodesic, can we find further new regions? Okay. So we can use the Timelike geodesic. Timelike geodesic I'm not doing, okay, because it turns out we can do it using something called pen-leaf coordinates, but it turns out it does not give anything new. So it's fine to work with only null as well as the space-like coordinate geodesics. Okay. So geodesics are my proof. Okay. I'm using geodesics saying by using a finite range of these quantities, can I create new regions? Okay. R star is not a good idea because R star, it's negative infinity as long as we go to the R equal to 2m. Okay. So we are using geodesics because which can go up to finite value of their affine parameter. And the question is that how long we can go? Can we create new regions in space-times which are still solutions of the Einstein's equation with the t mu nu equal to 0? Good. Excellent. So what we should do is that we should start with space-like geodesic, and exactly what we did for null geodesics, we should follow that. Okay. And this procedure is what is called analytic continuation. analytic continuation of the Schwarzschild manifold Z as Schwarzschild spacetime. And it turns out we can understand everything. Okay, we can understand all possible region, and I will not give you the full details of this analytic continuation. These are there in standard textbook, but I'll describe ultimately what are the regions we actually get. Okay, so let's start with that. Okay, so to understand this analytic continuation, we will define what is called the Kruskal coordinate. Kruskal, and then Szekeres or ERS, I think, coordinates. So these coordinates will be extremely good coordinates. Okay, and using these coordinates, we'll be able to do analytic continuation also using space like geodesics, and you'll find what is called the maximum analytic continuation of the Schwarzschild manifold. Okay. So the idea is that these coordinates we'll call them U and V. Of course, theta phi remains. We are not touching those coordinates. Okay. So we'll first define them, and then r greater than 2m. Then the trick is stem. You define first them r equal to 2m, write down the metric. If the metric everything is regular at r equal to 2m, then you can analytically continue it beyond r equal to 2m and define the quantities also inside. Okay, and the definition is this: u equal to e to the power minus small u by 4m, and v equal to Kruskal v equal to e to the power small v by 4m. Good. No. And then in this coordinate system, the metric is given by minus. So this I request you to check. This is not a very difficult calculation. You should be able to check it very easily. 2m du dv, okay, plus r square d omega square. Note that the way I have defined the Kruskal coordinates, these are null coordinates because this part is du dv. Okay, so UVs are null coordinates. U equal to constant or V equal to constant lines are null lines. Okay. See, generally x, y, z, t coordinates, x equal to constant line, y equal to constant line are generally space-like lines. Rather time-like lines. So you're moving along t directions. Okay. But here I am defining u and v such a way u equal to constant lines or v equal to constant lines are light-like lines. Okay. So that's the way we define the coordinates. You can also define by adding and subtracting, create space-like and time-like Kruskal coordinates. Okay, that is also possible. But the great idea of this coordinates is that the metric components are perfectly well defined everywhere, starting from r greater than 2m to r less than 2m. Okay. In fact, you can verify uv is e to the power minus r star by 2m, and that is by minus r minus 2m by 2m e to the power r by 2m. These are important equations. I sincerely request you that you should go back and derive this equation yourself. Okay, these are very easy to derive. These are just very simple algebra. Okay, so what we did is that we started from t r theta phi coordinate. We have gone into u v theta phi coordinates. Okay, my metric was initially f of r, 1 minus 2m by r dt square plus dr square by 1 minus 2m by r plus r square d omega square. Now Kruskal coordinates, this metric has transferred into ds square equal to minus 32m cube by r e to the minus r by 2m du dv plus r square d omega square. Okay, very well, we have coordinate system. And you can also check, okay, if r is greater than 2m, this part of the conditions is satisfied. U will be negative and V will be positive. Okay, so Kruskal coordinates are generally defined for r greater than 2m as long as u less than 0 and v greater than 0. Very good. Now let's write down the structure of spacetime in this coordinate system. So what we will do is that we write down this axis. So let's understand, if we look at immediately this coordinate system, it is clear r equal to 2m. What is r equal to 2m? Is either u equal to 0 or v equal to 0. Okay. So u equal to 0 line and v equal to 0 line represent r equal to 2m. Okay. So same surface r equal to 2m now mapped into v equal to 0 and u equal to 0. So let's draw. Again, as I told you, u equal to 0 and v equal to lines are 45-degree lines in this spacetime. They represent path of light cone. So therefore, this is r equal to 2m, as well as this is also r equal to 2m. Okay. So you may think of this as a u line on which v is 0, and this is a v line on which u equal to 0. And this is the origin they meet. At that point, u and v both are 0. Okay. How does the constant r lines represent? Look at this equation. This equation. They represent hyperbolae. Okay. So you can clearly see that as long as r is greater than 2m, this will be the constant r. R equal to constant, r equal to constant, but greater than 2m. Okay. Again, small r equal to 0 are the points where the curvature blows up. This is the singularity. It turns out Kruskal coordinate cannot be extended beyond that. So here, but r equal to constant is again, r equal to 0 is also an hyperbola. If you're inside, the hyperbola will look like this. So this is, let me not do that. Let's draw this. This is r less than 2m. Okay. So r equal to 0 will be somewhere here. So I'll draw this with wavy line saying that I cannot extend the manifold beyond r equal to 0. But not only that, this is just in the future. But in the past also, there is also another r equal to 0 line. This is the past r equal to 0, the past singularity. So this is r equal to 0. This is also r equal to 0. Again, in the past, there is this r less than 2m line. Okay. That's all. So in this region, u is less than 0, v is greater than 0. Okay. You should check carefully that in this region, inside, so this is what is called the region 1. Okay. You can go across the region 1, go into the future, and here you will be able to see u is positive, v is positive. This is what is called the region 2. Okay. Similarly, there is a region 3, which is exactly what we have found in the white hole case. And in that case, we will be able to see u 0, v less than 0. Okay. So that means, note, when we are talking about ingoing light rays, we were covering this particular region. Let me draw this. This bluish, this greenish shade line, this was covering by using ingoing light rays. Because ingoing light rays start from past and in the future cross r equal to 2m and goes to the singularity. Okay. When we were talking about outgoing light rays, let's choose another color. We were covering this region. I don't think this color is very clear, so let's cover this color. We were covering this region. Okay. And then what is happening? We are starting from singularity and going outward, okay, to the future. Okay. So outgoing light rays takes you from the singularity to the future. Ingoing light rays come from the past, in the future takes you to the singularity. Okay. So for the region 1, singularity is the future. Singularity is in the future, of ingoing light rays. Whereas in the region 3, or rather I would say, one should be a little careful. What I mean to say is that 1 plus 2, okay, and 3 plus 1, here singularity is in the past of outgoing light rays. Okay. So by ingoing and outgoing light rays, you can only go from region 1 to region 2 or region 3. Sorry, region 3 to region 1. Okay, that's all. But what is amazing is that there is also another region. Okay, let's find another color. What color? Yeah, this color. You can use a space like geodesics and go to a region, okay, which is completely new. Okay, so here is the region which is completely new to you, and in this region you can show that both u is 0 and v is negative. Okay, this is exactly a carbon copy but opposite of this region 1. Okay, and there is a new region IV. And what is this region 4? And region 4 is exactly similar to the region 1 and asymptotically flat. Flat universe. Good. So this is the maximum analytic continuation. It turns out you have exhausted all your geodesics, space-like and time-like and light-like. That's all what you have. So ultimately what you have after the maximum analytic continuation is the 4 regions of the Kruskal manifold. So the Schwarzschild geometry actually, when we are maximally analytically continued, represent 4 regions. Region 1 and region 2 are when ingoing light rays goes into the black hole. Region 3 and region 1 when outgoing light rays come out of the white hole. And there is a region 4 which is another asymptotically flat universe which is connected to the region 1 using this bridge at r equal to 2m. This is also, every point here is r equal to 2m. Okay, this is a 2-dimensional figure of a 4-dimensional manifold. So points, every point here represent a 2-sphere. Okay, I hope this is clear. Okay, so what we have done, we have created full maximum analytic continuation of the Schwarzschild manifold, and this is what is called the Kruskal extension. And we have found that there are new regions. Okay, so I'll wait here. If there is any question. If there is any question, please. So you can write to me in the chat. I'll look at it. So basically what we are doing is that we are geodesic and looking for the affine parameter of the geodesic, finite value of affine parameter, how far we can go. Okay, this is called the analytic continuation. Okay. You can actually look at the Kruskal manifold. Let me draw the Kruskal manifold a little bit again. The causal structure. These are r equal to 2m surfaces. Okay. You can think of this as an outside static observer. Let's say r equal to 5m. Okay. It will be uv equal to constant, so this will be an hyperbole. You can think of this as a infalling observer. Okay, an infalling observer which is falling into the singularity. Okay, now suppose I ask you that can the infalling observer communicate with the outside static observer? So it communicate by sending light rays, and in Kruskal diagram light rays are 45-degree lines, radial light rays are 45-degree lines. They look like this, but once they're inside, okay, if they send a light ray, it will never reach the outside static observer. Okay, because light rays must be 45-degree line parallel to the v equal to 0 or u equal to 0 line. Okay, this is r equal to 2m. Okay. So that means the causal structure is evident here. Once you are inside, you cannot send anything. Okay. So you are trapped. So all the light rays you are say before you hit the singularity will never come out of the r equal to 2m surface. Okay. So how the analytic continuity differ when you use space. So note that in space, using space-like geodesics, so this is the space-like path. You can come to the region 4. Okay. That's the whole idea. Okay. So using space-like geodesics, so time-like geodesics and light-like geodesics can cover region 1, 2, and 3. But using space-like geodesics, we can come out to the new region, which is called the region 4. And it turns out that region 4 is also asymptotically flat universe. So the full structure is that there are two asymptotically flat universes connected through this bridge at r equal to 2m. And this r equal to 2m bridge is actually called the Einstein-Rosenberg bridge, because two of these guys is the first time identify it. But it turns out that you cannot cross this bridge. This is a first example of a non-traversable wormhole. It's a bridge, but it turns out if you want to cross it, that this bridge will close before you move out from one universe to the other universe. It's a non-traversable wormhole. Okay. If you want details, of course, I'm not going to cover those details here. The best place is to look at the book by Mr. Wheeler-Thorne, the fat book, Gravitation, which is a beautiful picture explaining what will happen if you want to go from one side of the universe to the other side of the universe, okay, using the r equal to 2m bridge. And it turns out you cannot do that. Okay. The bridge will never be open for a longer time that you can cross it. Is there any other question? Good. If there is no more questions, we will go into the next topic of our lecture. Okay. And we have understood the maximum analytic continuation. Yes, you can say that. Yeah. So let me look at the new part of the thing where we will start understand how does test particle moves in the Schwarzschild geometry. Okay. So let's start the part 2. Okay. So for most of the discussion, see, the Kruskal extension is just a mathematical extension. Okay. When we are in the gravitational collapse, the past is the inside of the gravitational collapsing ball. In that case, the Kruskal extension is no longer valid because Schwarzschild solution is only a vacuum solution. Inside the ball, the vacuum solution is no longer valid. There is a matter there. Okay. So therefore, for most of the cases, when we look for the motion of the test bodies, it's only the region 1, Kruskal 1, which is what will be relevant to us. Okay. So we want to study how test particle and light travel in the Schwarzschild spacetime. Okay. Now the answer is already given to you. Okay. When we have discussed the basic premise of general relativity, we have discussed that test particle travels in geodesics. Light travel in time-like geodesics, and light travel in light-like geodesics, and massive objects like physical particle like electron and me and you and the planets, if they're test object, they travel in time-like geodesics. Okay. If you could move faster than the speed of light, like hypothetical particles like tachyons, they will travel more than the speed of light, and therefore they will travel in space-like geodesics. Of course, physically nothing travel at space-like geodesics. Okay. So basically the idea is that massive particle, that means things which have non-zero rest mass, massive particles, move along Timelike geodesic. So this is the dictum which John Wheeler taught us long ago. Okay, matter makes the space-time curve, and the curved space-time tells the matter how to move. Matter makes the space-time curve using the Einstein's equation, and it is the geodesic equations which tells how the test matter in that curved space-time moves. Okay. I give you equivalency in Maxwell's electrodynamics. Maxwell's equation tells us, given the charges and currents, what is the electric and magnetic field, right? The Lorentz force law tells us, given the electric and magnetic field, how a test charge moves in the space-time. Okay. So basically, it's the same thing. The geodesic equation, in some sense, plays the role of the Lorentz force. But you have to be a little careful that there is not exact analogy. We are talking about a curved space-time, and we are talking about a geodesic in curved space-time. Okay, there is hardly any force acting on the masses. Okay, and the geodesic is a curve x alpha. Since it's a timeline, let me, for brevity, use the proper time as the parameter on this curve, and then I define the force velocity will be dx alpha by d tau. Okay, and the geodesic equation is nothing but u alpha del alpha u beta equal to 0. Okay. If you do it in flat space-time, you can always use the Cartesian coordinate system. Then this is nothing but saying the acceleration is 0. Okay. But in curved space-time, of course, we have to be careful and you have to use the most general equation. Good. And then this equation, we can write it open it and write it as d square x alpha by d tau 2 plus gamma alpha beta delta dx beta by d tau dx delta by d tau. Okay. Okay. So what one should do is that I give you the metric, which is the Schwarzschild metric. You calculate the gammas, write down the geodesic equations, solve them by using appropriate boundary condition, get all possible timelike geodesics. Of course, you can do that, and it is not a difficult thing to do, but note that this is a second order differential equation. Okay. While the symmetry of the problem, the spherical symmetry and time symmetry of the problem already has given you conserved quantities. Okay. So this conserved quantities is in some sense the first integral of the motion. So basically you can use these conserved quantities to convert the problem from a second order differential equation solving to a simple first order differential equation solving. This also happens in Kepler problem in Newtonian physics. And this is exactly what we are going to do. Okay. And then the calculations will be much more simpler by using the conserved quantities. Okay. So let's understand what are the conserved quantities. So first of all, I like to know the Lagrangian of a massive particle. Okay. So I'll write down the Lagrangian of a massive particle in this space-time. We will set the mass of the particle to 1. Okay. You can set it to something, but just for simplicity, we'll set it to 1. Lagrangian of the massive particle. Okay, and that Lagrangian will be, we already know this is nothing but the dx mu by d tau, dx nu by d tau. Okay, this is the Lagrangian of the massive particle. Okay, is integral multiplied with the time integration over with respect to the property will give you the action. Okay, and we will introduce G mu nu instead of G mu nu. We'll now have the Schwarzschild metric. The background space-time is Schwarzschild. So this Lagrangian is now given by minus 1 minus 2m by r, okay, t dot square plus 1 minus 2m by r whole inverse r dot square plus r square theta dot square plus sine square theta phi dot square. Okay, and of course t dot is dt by d tau, r dot equal to dr by d tau, and etc. Okay. This is our notation. Okay, good. Question is, what are the conserved quantities? We already know what are the conserved quantities. There is a time translation invariance, time invariance. Lagrangian does not depend on time, and therefore the energy is conserved. Sorry, I mistake. Energy is conserved. Of course. There is also phi symmetry, okay? Nothing depends on phi's. There is azimuthal spherical symmetry, and therefore there is a angular momentum conservation. Momentum conservation. There's also a trivial symmetry, trivial conserved quantities. I'll think about it later, okay? So the problem will actually simplify quite a bit. Remember that even the central force problem, we started with a three-dimensional motion. The central force problem turns out to be a planar motion. Okay, this is exactly what will happen here. So let's understand why. Okay, so we want to know how the particle is moving. So basically, given this Lagrangian, we will write down the Euler-Lagrangian equations. Okay, let's understand the theta equation. Theta equation. How does the theta equation look like? Of course, we all know that this is del L del theta minus d d tau del L del theta dot equal to 0. This is the theta equation. And if you calculate this theta equation from this Lagrangian, you will be able to show that this theta equation will look like r square theta double dot plus 2 r theta dot r dot theta dot equal to r square sine theta cos theta phi dot square. Good. Now what I do is that initially I set the particle at initial point at theta equal to pi by 2 and say theta dot equal to 0. These are my initial condition. Okay. Immediately you will see that theta double dot equal to 0. Equation is this. Okay. That is a remarkable fact, which means if I can fix the particle at theta equal to pi by 2 and theta dot equal to 0, theta double dot remains 0. That is, theta dot does not change. Okay. And theta remains at pi by 2. Okay. So it means initially, if the particle is on theta equal to pi by 2, and that is exactly what the equatorial plane is, that the particle remains in the plane. Okay. So therefore, if we set theta equal to pi by 2, the particle remains in the plane. Now there is no particular special. We can always choose the origin any tilted. So we can choose any plane as theta equal to pi by 2. So it means the system is planar. Okay, the motion of the orbit is planar, two-dimensional. And this is basically the consequence of the angular momentum conservation. Okay. So therefore, without any loss of generality, we can always set theta equal to pi by 2 and simplify our calculation. Okay. So we can set theta equal to pi by 2. Basically, we are saying that our coordinate system is such that our equatorial plane is theta equal to pi by 2. And all the physics is happening there. Okay. So take any plane in which the particle is moving, call that plane is equal to theta equal to pi by 2 and arrange your axis such that. Okay. So we can always set theta equal to pi by 2. This is the characteristics of the central force problem. Okay. And then our Lagrangian has simplified to, my mistake. Let me write it down. So theta equal to pi by 2, theta dot goes away from the picture. It is only the problem of 3 terms. Okay. These are the 3 terms which are relevant for the physics of the problem. Okay. So let's understand time translation invariance, time invariance. So again, the physics should be clear. We are thinking about a test particle in this background space-time outside the black hole. Okay. We are not concerned about what is happening inside. Okay. At the end of the day, what do you want? Look at this picture. Okay. This picture is the something we like to understand at the end of the day. For that, we need to know how light is moving. Okay. First, we'll understand how the particles are moving, and then we'll generalize it to the massless particle and understand the notion of black hole shadow. Okay. Good. So time invariance simply means del L del T equal to 0. Nothing depends on time. Okay. So therefore, what it means is that d d tau, this is the T equation, del L del T dot equal to 0. Okay. And if you do that, you will immediately find that you will see d dt tau, and if you calculate del L del tau, the answer will be minus 2m, sorry, 2, no m, sorry, my mistake, 1 minus 2m by r t dot equal to 0. So what it means is that this object is a constant. Okay. And what do we call the constant when we are talking about time invariance? The constant we call energy. So what it turns out, it means that, so we generally take away the -2 part just to relate the conventional energy expression for energy. So we'll call it 1 minus 2m by r t dot equal to constant, and that constant we call E. So throughout the motion, so let's say E is the energy, 1 minus 2m by r t dot energy. Okay. Now note that if the particle is moving on a curve, let's say x alpha as a function of tau, r is changing because it can go decrease or increase the r. Okay. So this is changing. Again, t dot is also changing because if it moves in space and time, t will change with respect to the proper time. Okay, because it's moving in the direction of future. But the change is such that total product remains always constant. Okay, that's the requirement of the time translation invariant. Okay, now this looks like a bit odd expression for the energy. Okay, this looks like a very odd expression of the energy. What we can do is that let us understand that whether it is actually the energy, okay, by going into the flat space-time limit. Okay, so what you can do to check if this is indeed the energy, take the limit, let's say r goes to infinity. That means you are very far away from the black hole. Oh, I mean central object. For that matter, we don't need to be a black hole. Okay, as long as it's a central, sun is also good enough. Okay, so we are far away from the sun. In that case, the energy is, so we can ignore 2m by r term because r goes to infinity, 2m by r goes to 0. So in that case, it is t dot but evaluated at infinity. Okay. Okay. Now we have set c equal to 1. Speed of light is set to 1. And you know that proper time d tau in flat, see, away from the black hole or the compact object or the central object, we are very far away. So we can think of using special relativity equations. Okay. The metric is asymptotically flat. It reduces to the flat metric when you are far from the black hole or the central object or the central compact object. So therefore, we are free to use simple special relativistic equation from the large distance, okay, at the large distance. And that equation is nothing but 1 minus v infinity square. This is the velocity at large infinity into dt. Okay. Okay. Note that there is a v square by c square. We have set c equal to 1. Okay. Now, what it means is that E is t dot at infinity, which is dt by d tau at infinity, and this is nothing but gamma at v infinity, where gamma equal to 1 by square root of 1 minus v infinity square. Okay. In fact, if you add all the c square and everything, then you can show this E is nothing but v as v infinity into c square. Okay, which is exactly the relativistic energy in special relativity of a unit mass quant. Okay, relativistic energy of a unit mass and unit mass object. Said that if you're in the rest frame, gamma becomes equal to 1, then you have mc square, okay, or c square. Here m is 1. Okay, m here, when I say m, this is the mass of the particle, not the central object. Okay, good. So therefore we come back to the, so we ensure that this expression is indeed matches with our notion of energy. Good. Okay, so we have understood the energy. Very good. Interestingly, there is also another invariant object, which is the angular momentum. Okay, so that comes from the invariance del L del phi equal to 0. Nothing in this Lagrangian depends on phi. So Noether theorem ensures that there must be conserved quantities. And if you calculate that conserved quantity from this equation, this is nothing but d dt by Euler-Lagrangian equation del L del phi dot equal to 0. Okay, and this is by d dt of 2 r square phi dot equal to 0, and therefore we define L equal to r square phi dot. We call it angular momentum or unit mass actually, but anyway, constant. Okay, but so we have found the energy, we have found the angular momentum. Note that angular momentum is a vector, but since we have chosen a plane, this vector is basically 0, 0 this. Okay, so it becomes all the other two components are 0. Okay. There is also another nice, interesting, very trivial conserved quantity. Okay, so let's understand that conserved quantity. Okay, so let's say I want to know how the Lagrangian itself changes along a geodesic direction. So what about change of the Lagrangian along the direction of the tau? That means u alpha del alpha Lagrangian. Okay, so you move along this direction of the curve. You want to know when you move along this u alpha how the Lagrangian is changing. Okay, the answer is obviously Lagrangian will not change, but let's see. Okay, so that means this is u alpha. So okay, del alpha, and Lagrangian is g mu nu x mu dot x nu dot, usual notation of the dot, what we have done last time. And this is nothing but g mu nu. Remember, g mu nu, when it acts on the covariant derivative, the answer is 0, because metric is, the connections are chosen to be compatible with the metric compatible connections. So therefore covariant derivative does not act on the metric, gives you 0, and you are left with something like this, x mu dot, and this 2 factor comes because there are 2 x dots, and then u alpha del alpha u nu. Okay, because u nu is x nu dot, and again the geodesic equation set this quantity to 0 by geodesic equation. So therefore what we have found is that L alpha del alpha Lagrangian is equal to 0. So the value of the Lagrangian actually does not change when you move along the geodesic. Okay, this is a trivial conserved quantity. This basically says that is because this Lagrangian is related to whether the curve is space-like or time-like. So basically what is happening is that you can always normalize this Lagrangian to +1, -1, and 0. So what it means is that a time-like curves remain time-like, space-like curve remains time-like, remains space-like. There is no continuous change by which you can convert a time-like curve into a space-like curve, and vice versa. And of course to null curve. Okay, these limits will be discontinuous. Okay. What we do is that we set Lagrangian to some epsilon. So epsilon equal to -1 is time-like. These are the 2 cases only we are interested. Epsilon equal to 0 is light. Okay. These are the only 2 cases we are interested. Okay. So therefore, let's now write down our Lagrange equation. Our equation then ultimately looks like r t dot square plus 1 minus 2m by r whole inverse, and then r dot square plus r square phi dot square equal to epsilon. Okay, good. Now we want to understand how to convert this equation by use. So technically we don't want to even integrate it because we already know the constant of integration, E, the first integral of the motion. So we'll just use 2 other equation, the definition of E, 1 minus 2m by r into t dot, and L equal to r square phi. What we'll do is that we'll find solution in terms of E and L. Okay, that's all. Okay, if we do that, we will get, so this 2, substitute it here, and then what you get is this. Okay, you get minus, this is a simple algebra, I'm sure you'll be able to do that even better than me. So I'm not doing it. Minus 2m by r whole inverse r dot square plus L square by r square equal to epsilon. Okay. Again, you can simplify everything, and ultimately turns out the simplification will give you a result E square plus epsilon. Do not miss between E and epsilon. My handwriting is bad, but to be careful, equal to r dot square by 2. Okay. Remember, the dot is with respect to the proper time, epsilon m by r plus L square by 2r square minus ml square by r. Excellent. Now let us define things. Okay, define just a definition. Okay, E effective, and that we call denoted by E square by epsilon by 2. Okay, and we call V effective R as epsilon m by r plus L square by 2r square minus ml square by r. Okay, these are the two quantities we define. And therefore, we find that the equation, okay, the Euler-Lagrangian equation, the R dot equation, ultimately reduces to a very simple equation: E effective equal to half R dot square plus V effective. So let's box. If you now recognize that R dot square is nothing but the, in some sense, the kinetic energy, it's a little bit different. Dot is not really with respect to time. It's with respect to the proper time, okay? But so in some sense, this is exactly equivalent to one-dimensional Newtonian motion under the potential V effective R, okay? So this is equivalent. This is identical to the case of a 1D Newtonian motion under the potential. So what is the potential? The potential is V of R equal to, so except this part, I will explain this part. This is nothing but epsilon m by r minus, sorry, not g, m L square by r cube. Remember, this capital L is the angular momentum. Okay. So therefore, what we have found is that we have equation E effective equal to half r dot square. There is no m r dot square. This m is set to unity. Okay. This particle is a unit mass particle plus epsilon m. No, let me write down the first this part. L square by 2r square, and then part V of r. Okay. So if you remember your central force problem, we have converted the GR problem into a classical central force problem in Newtonian mechanics, okay, with a potential V of r. Okay. So there is equivalency. The GR problem can be mapped into Newtonian problem, but not with 1 by r potential. See, the planetary motion is actually 1 by r potential. Okay. But what we have found, we have an extra term. Okay. Extra term. Okay. So GR is equivalent to Newtonian's theory, but with an extra term ml square by r cube. Okay. And this is actually the relativistic term. So let us now, what we do is that in the effective potential, let's bring out G and C, and let's see how the potential VR look like. If you do it for the case epsilon equal to -1, the time-like case, the usual planetary case, you will see this will look like Gm by R minus Gm by L square by C square R cube. Okay, I'll explain in the new class why the C square come. Note the appearance of the C square. In ordinary Newtonian theory is a non-relativistic theory. There will be no C square. Okay, but GR gives you a correction term which is proportional to 1 by C square. Okay, so this term is the This term is the correction term to the Newtonian theory, and it comes out of the dynamics of general relativity, and the appearance of C square clearly shows the origin is relativistic. So this is relativistic correction. Relativistic correction. And next class, I will talk more about this term, but today I will stop here because there is another lecture. In the next class, we will talk about the application of these formulas to understand what is called the light-like geodesic or the path of light ray.